Good morning, kids. Well, since the last time I talked to you, I've become a mom again, so I'm pretty pumped about that. I have a beautiful baby girl, and her name is Mary Elizabeth, and she's doing just really great. And I could not be more blessed, so I wanted to tell you that, and there are pictures coming your way, so no worries. Today, we're going to talk about some common Taylor series. We have about 6 or 7 here that are the most common that we will see on the AP exam. These are Taylor series about x equals 0, and they basically are polynomial functions that well approximate these functions around 0. And of course, the further that we go out, the more terms of the Taylor series that we see, then the closer we get to the actual value of the function. I hate that little message that pops up about the color scheme. It trips me up every time. So moving forward, so these are the bunch of functions that we have. We've got one for e to the x, pretty simple to remember. Sine x starts with x, it's got an alternating sign, odd powers of x, the factorials match the powers, and then we've got the cosine, again alternating signs, starts with 1, even powers of x and the same factorials. And then I put one on there for 1 over 1 minus x, which is really simple. It's just basically powers of x. And then 1 over 1 plus x is alternating powers of x. Finally, one for the natural log of 1 plus x, and that's basically powers of x over the number of the powers. So it's x to the first over 1, x squared over 2, etc. And that also has an alternating sign. So those should be not terrible to remember. You should memorize all of them. They will make your lives much easier if you memorize that bunch of things, because if you memorize them and then you're asked, for example, to do cosine of x squared, then you could just use this cosine of x function and you can plug in an x squared for your x. It just makes life a lot easier when you're going to generate a polynomial. You don't have to go through taking all of the derivatives and finding a pattern, etc., etc., like we did in the last class. Now, mind you, if you were to forget one of these and you had to have it, you could generate the polynomial like we learned to do in the last class. So that's still good to remember, because if you get stuck on one of these, it'll always work. So I'm going to move on. The remainder theorem I'm going to come back to later. Basically, that tells us what the error in a Taylor polynomial is. So I'm going to come back to that in a little bit. Bottom line is, each term in a Taylor series will bring us closer to the actual value of the function. So important to note. So here's our first example, and I ruined the suspense because all of the information is already down there, so I'm going to have to erase it in front of you, and then we'll do it together. So I hate when I ruin the suspense like that. There's that. Alright. I hope I haven't blown the whole class for you all by ruining the suspense. There we go. Now I have e to the negative x over 2, or e to the negative 1/2 x power. And I'd like to, these are examples from page 468, by the way. What I'd like to do is just generate the Taylor, actually the Maclaurin series, the Taylor series about x equals 0 for this. So what we're going to do is we're going to use the fact that we know the formula, theoretically, for e to the x. So here's the formula for e to the x. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Now, instead of doing those powers of x, what we're going to do is, you see how I am putting parentheses around all my x's, and instead of those x's, I am going to plug into the parentheses negative x over 2. And what that will do is it will allow me to generate a Taylor series for e to the negative x over 2. So here we go. E to the negative x over 2 then would be equal to 1 stays 1 no matter what, and then plus negative x over 2, and then plus negative x over 2 squared over 2 factorial, and then plus negative x over 2 to the third over 3 factorial. And then you just do the plus dot 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 to indicate you're going to keep going with that. And now we're going to simplify, and we're going to see if we can find some sort of a pattern. It's always good to look for the pattern. Alright, so we have e to the negative x over 2 ends up equaling, well, we have 1 for the first term, and then minus x over 2 for the second term, and then plus for the next one, because you're squaring the negative, x squared, and then you have 2 squared times 2 factorial. That seems like kind of a good thing to have in the bottom, so I'm going to leave it as 2 squared times 2 factorial. Because we're not going to have anything left in the top to cancel the factorial, so my guess is we want to keep the square and the factorial in their form in order to find the pattern. And then the next sign is going to be negative x cubed, and then on the bottom you're going to do 2 cubed times 3 factorial. And if you check this out, it looks like a fairly simple pattern. Let's see what the n's are here. This is n equals 0, and then 1, and 2, and 3, etc. And if you look at that, you can see that the n's and the powers of x's and the factorials and the powers on the 2 in the bottom are all matching. So you're going to say e to the negative x over 2 is equal to, trying to generate the formula, the sum n equals 0 to infinity of negative 1 to the n power, because the first one is positive, and if we do negative 1 to the 0 we get positive 1, right? And then x to the n, because your power on x is always matching your number on n. And then in the bottom you're going to have over 2 to the n power times n factorial. And you're set. So that one wasn't too bad, really. Let's go on to the next and see how it goes. Here I go. I'm going to ruin the suspense yet again. Let me erase this real quick, and then we'll do it again. I'll have to remember to do that in the future before I start. Usually I can mute my AV device and do that, but this is a whole new world for me, talking to a computer instead of talking to people. So this next one, x squared cosine x squared. Now this one is not only your cosine Maclaurin series, but then you're going to multiply that series by x squared. So you got some crazy stuff going on here. First, let's write the series for cosine x. So cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. Now what we're going to do is we're going to plug in for x again. Instead of x in each of these, make sure you put parentheses, because when you have negatives it gets kind of tricky. Alright, oops, I forgot to make this a negative sign over here. This is alternating signs, so that should be a negative there. So now we're going to plug in x squared for all our x's. That'll be our first step. So let's go ahead and do that. We say 1 minus x squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial. And then we have to multiply that, of course, by x squared out front. So now what I'm going to do is I'm just going to put an x squared in front of my cosine x here. And then basically what I do when I multiply both sides by x squared here is I'm taking that side, and I'm distributing an x squared through the whole thing, right? So, wait a minute, I should put these on here. So what I'm doing is distributing an x squared through the left side and the right side. When I do that, I get, for my first term, x squared. For my second term, I have x squared squared, which is x to the 4th, right, times x squared, so that's x to the 4 plus 2, or x to the 6th, over still 2 factorial. And then the next one is going to be x squared to the 4th, which is x to the 8th, and then times x squared. So we add 2 to the exponent, we get x to the 10th over 4 factorial. And then minus x to the 12th, and then you've got this 2 squared over here that it gets added, so it's x to the 14th over 6 factorial. And then plus, and it continues. Now, what would the pattern for this be? Well, you should always be looking for these patterns. I know you're always worried that I'm going to ask you this on a test and you're not going to be able to do it, but honestly, these are not that hard to find. Now, this pattern, because as our powers on x are going up by constants here, we go 2 to 6 to 10 to 14. So if we just take 2 points here, if we match up some ordered pairs, if this is n equals 0, and then 1, and then 2, and then 3, etc., okay, all we really need is, in order to get this, since it's linear, is to have a point and a slope, okay? So the point, the first point we're going to do is we're going to look at what the y-intercept would be, looking at n as like an x-coordinate and the powers on your x's as y-coordinates. So if you look at the powers on x's as your y-coordinates and you're trying to figure out what the y-intercept would be, it'd be what is the power on x when n is equal to 0. So this is going to be the sum n equals 0 to infinity of x to the, well, the y-intercept, for lack of, oops, where'd it go? Come on back. The y-intercept, for lack of a better term, here would be 2, right? So if we're trying to generate a formula just for the powers on x, b is going to be equal to 2, and then your slope is just the difference between your powers on x. So the slope here is 4. Okay, so if you want to figure out what this is, it's x to the 4n plus 2. Because the slope is 4, your n is like your x, and then your y-intercept is 2. Okay, so that's your top. That's the harder of the two. Now your factorials in the bottom here, you would think of the first factorial as 0 factorial. So this one, the y-intercept for the bottom factorials is 0. Okay, so for your tops, let me match these up a little bit to the formula. So this generates the top formula, and these b equals 0 for your bottom formula, and then your slope on the bottom would be, well, you're going up by 2 each time on your factorials, so your slope is 2. So basically what you have is a slope of 2, y-intercept of 0, so this is 2n. Now be careful, it's got to be in parentheses, factorial. And then one thing I forgot is negative. Since the first one term is positive, we do -1 to the n, because -1 to the 0 is 1. So that would be your pattern. Now, a lot of times it won't ask you for the pattern, but I'm all about the pattern. You need to be looking for that on the AP exam. You will be asked those types of questions, so it's important to know that. So I'm going to just do 2 of those types. I think those are pretty simple for the most part. Now we want to go up and talk about error a little bit. The error in a Taylor series is basically, it follows this formula. This is what we call the remainder theorem. And basically what it says is the error in a Taylor polynomial is less than the maximum value of the next term. Now, if you think about Taylor polynomials, you remember that it was all based upon the derivative, the power of x, and then the factorial in the bottom. And they were all the same. All right. So if you want to know what the error for the nth degree Taylor polynomial, what you do is you look at the n plus first term. Since every term gets you closer to the actual value of the polynomial, when you look at the n plus first term, you're looking at basically the maximum error that you can have in the polynomial. So we're going to take this remainder theorem here and we're going to utilize it. Now m here stands for the maximum value of your n plus first derivative, of your next derivative. And then x minus a to the n plus 1 over n plus 1 factorial. That's just the formula for the next term. Okay, so the key is finding the maximum value of that n plus first derivative. And if you have your known Taylor polynomials, like up on this page, it's much easier to find this remainder error. So let's look at an example of this. Now this says if cosine x is replaced by 1 minus x squared over 2, and the absolute value of x is less than 0.5, what estimate can be made of the error? Well, let's look at the Taylor polynomial for cosine of x, about x equals 0. That is cosine x equals 1 minus x squared over 2 plus x to the 4th over 4 factorial. Now this x to the 4th over 4 factorial, x to the 4th is an increasing function, so this term is going to be greatest when x equals 0.5. Okay, so you're looking at the absolute value of x being less than 0.5. So we're looking at this function only between -0.5 and 0.5. What would be the maximum value of that next term between -0.5 and 0.5? Well, since this is an increasing function, x to the 4th, the maximum value would occur when x equals 0.5. So that's what we're going to write here, that the greatest value of this is at x equals 0.5. Alright, so what we're going to do is we're going to figure the error. The error must be less than the value of this term. And I'm going to write this down so you less than the value of this term when x equals 0.5. Okay, so all we really need to do to figure out this error is we're going to stick in, we're going to plug in the 0.5 to the next term. right? Because we've got the first two terms. The error in the first two terms has to be less than the next term. So we plug in that 0.5. Oh, also, this estimate, we want to know, is it too small or too big? Well, the estimate is too small. The reason the estimate using 1 minus x squared over 2 is too small is we add the next term. So in order to get closer to the value, we're adding something. That means the estimate must have been too small. Okay, so the estimate is too small because the next term adds something rather than subtracting it. It increases the value. That would be a better way of putting it. So the value of this is increased when we put the next term in. So that means that 1 minus x squared over 2 is an estimate that's too small. So let's find that error now. The absolute value of x, is less than 0.5. So the error, and I'm just going to use ER for error, is less than 0.5 to the 4th power over 4 factorial. So the error is less than 0.0026. That's really all there is to that. I mean, it's not, it's confusing. Sometimes people find it to be confusing. I don't think it's too bad. When I first learned it, though, I'm not going to lie, I found it to be confusing. So the focus should be not on the weird formula, but rather on thinking about the next term of the Taylor polynomial. It makes it a little easier to understand and maximizing that next term. So that's really all I'm going to do today. I have for you some homework, and if you guys, the smart thing for you to do is to work on this homework while you're in class. I mean, you have tons of extra time in class, so you should try to work on the homework while you're in class, and then it will make your life a little bit easier. So your homework is page 468, 1 through 11 odd, 17, 19, 21, and 25. I hope you have good luck with this. I do have another error example, which is on the next page. It's really basically the same as the one I just did, and I am going to post it with the notes online, so you can look that over. But again, you know, the video gets so long if I do every example, and I think you should be able to understand this this next one. It's very well explained in the next page here, and I'll post it online. So thanks so much for listening, and I hope that that it wasn't too confusing for you. If you have questions on the assignment from last class, I can take 1 or 2 of them. What you need to do is give them to whomever it is that's keeping you company, and they will get them to me, and I will address them in the next lecture that I do. So if you've got major questions, and I think maybe last class you won't have had questions, but definitely this class you will probably have questions, so send them my way when you have questions, and I will be glad to answer them. Just refer to the page number that you need, and also the question number. All right, have a great day, kids, and I'll be sending pictures of my girl. Bye.